All right. Hi, everybody. Welcome to reInvent 2024. I think this is a point where you can put your headphones on. We don't have any microphones except for this one, which I think is going directly into your headphones. Can everybody hear me okay? We good? Way in the back, too. Perfect.
All right. You can hear me okay, too? Yep. All right.
Sweet. Just to make sure you're in the right spot, this is DAT320. We're going to talk about supercharging app intelligence using GenAI with Amazon DocumentDB. GenAI, who has already been to 12 GenAI sessions at reInvent this year? That's right, right? I feel like we should have a drinking game. Every time I say GenAI, you drink water. It's 11:30 in the morning. You people are crazy. So today, what we're going to talk about is a little bit different than maybe some of the GenAI sessions that you've gone to. We're going to talk about GenAI on DocumentDB. We're going to start off, we're going to set the foundation on vector search. What are the key words? What are the key components of that? And then we're going to go into access patterns, especially access patterns that we're seeing DocumentDB customers use. Then we're going to talk about vector search specifically on Amazon DocumentDB. We're going to talk about how it works, how we set it up, really the way that it works, because this is going to become very important when we talk about creating modern search operations and then best practices for it. Again, heavily focused on the database side of GenAI. We're going to touch lightly on LLMs and options that you can use, but very, very deeply focused on this. This is a 300 level course, so we're going to assume that you are familiar with DocumentDB. You don't need an introduction to it. You know what a document database is. You know what a JSON model is. If you can't see us way in the back, this is what we look like. I'm sorry, potentially. I'm Cody Allen. I'm a principal DocumentDB solution architect. I've been with the team for about 4 years now, based out of Dallas, Texas. And with me is...
Doug Bouncer, and everything else is the same.
We're interchangeable.
We're interchangeable.
Dallas,
Texas, been with the team about 4 years.
What is that called? High availability for essays?
Failover.
Who's the primary and who's the secondary? We'll answer that later.
Yeah.
So let's start off talking about vector search. Now, the concept behind vector search, I'm sure you're aware, is to build, search, manage, expand, use vector embeddings on a database. Now, you're going to perform a vector search on top of those embeddings to give you a contextually relevant answer. It's going to be different than a binary search where you're doing a text search looking for a phrase. You're looking for context. You're looking for recall or relevance. There's a lot of options for databases that you can use. We've announced vectors on OpenSearch, on DynamoDB. There's Pinecone. There's third-party tools you can use. We have vector embeddings on DocumentDB now. It's really important to choose the right vector database that meets your use case. You want it to be secure. You want it to have the most contextually relevant results, and you want it to be close to your data. These are all big important factors to consider. Now, the whole purpose is, well, retrieve those items that are contextually relevant to your data. Vector databases, vector search, vector embeddings. We're going to start a new drinking game. Every time I say the word vector, you drink your water. But let's start off with vector embeddings. That's really the key thing that we need to focus on for this talk. You start with your data, your domain-specific data, and you're going to break that into different elements. And those elements are going to hold meaning on their own. That's called tokenization. Now, those elements, they can be words, they can be paragraphs, they can be sentences, they can be entire documents. Really, it's up to you what makes sense for your use case. But now that you have all of those different pieces, all those elements, you're going to pass them through a large language model in a process that is called tokenization. And that is going to turn those elements into essentially really, really big arrays of numbers. You'll have different options based on your LLMs. You can have some that are as few as 200 numbers, and you have some that are over 4,000 numbers. Again, this really depends on your use case. Those numbers exist in this multi-dimensional space, right? Where items that are similar are going to be somewhat closer to each other. And what that means is that to find a semantically similar result, it's just a mathematical function to find the distance between two elements. But again, the whole thing, the whole process here is to choose the right options that meet your use case and create those embeddings. That's what it all comes down to. So just to make sure that you caught all that, there's a lot of pictures on that, a lot of words. Where does it start? Does anybody remember where this whole process starts? I would say that one more time. Embeddings. But those embeddings come from your data. Everything here starts with your data. That's what makes it so significant. That's what's going to be the difference between having a generic generative AI app like something like a ChatGPT to one that knows your business and that knows your customers, right? Everybody here has access to the same LLMs, the same foundational models. I think we just announced a couple earlier. Gosh, what were those called? Something like real and text and.
Yes.
I love reInvent. It's a lot of fun. We always learn about new things, but most often, everybody here learns about our services before we do.
Yeah.
A lot of times,
you all know more than we do.
Yeah, a lot of times customers will say, "Hey, tell me more about that new service, AWS Beluga Whale." that's not real, right? It's real. Is it what? Nova. See, that's exactly what I'm talking about. Nova. That's awesome. But having your model, having your data go through those models is really what makes the difference. But the great thing is you don't have to train your own model, right? That's why we have all of those out there. But you use your operational data to fine-tune these models through a process called RAG, Retrieval Augmented Generation. So as an example, let's say that you run a shoe store, right? And you create a chatbot to help people out. You have somebody come to the chatbot and they say, "Hey, I need to return my shoes for a full refund." Well, this is where your operational data store comes in. First, the agent is going to go do a fact lookup. They're going to go look at your orders table to find the order information for this person. They're going to go look at the inventory table to find, well, do I have any more of that shoe in inventory and what are some other shoes, right? Next, the agent is going to do a vector similarity search against your table that holds policy documents, right? Maybe you have policies that say, if an order was made greater than 30 days ago, there's a 10% restocking fee. Or maybe if it was made within 2 weeks and they're returning it, they can return the shoe for a full refund, or we can replace it. And the shoe that we would replace it with is out of inventory, so maybe we look up shoes that have a similar heel drop or similar width or size, right? You're doing a similarity search against your data, that knowledge repository, to be able to make a decision for this customer to return their shoes. That is a high-level concept of RAG. So Doug's going to walk us through an example architecture so we can understand how those pieces fit together a little bit better.
All right, thanks, Cody. Mm-hmm. So let's take a closer look at what this might look like, this retrieval augmented generation or RAG architecture. So in the context of Cody loves sneakers, in case he hasn't said so.
Anybody a sneakerhead here? Yes, my people.
All right.
Awesome. Go over to Caesars. There's some really good shoe stores over there. Nike has some pretty good dunks. So even some on special, 30% off. But I digress. Go ahead, Doug.
No problem. So Cody got some sneakers and for some reason he might want to return them. All right. So in the context of this architecture, just kind of go over the flow of what this might look like. All right. So Cody here, he interacts with a GenAI application, typically by posing a question. So maybe he's asking, "Hey, can I return these sneakers, right? They don't fit quite right, or they're not the right color. They're just not what I was expecting." So what will happen in this type of architecture? First of all, this application is going to access a data store for any conversation history. Right, if maybe Cody's interacted with the agent before or earlier in the conversation, right? If this is maybe some sort of multi-step conversation that goes on over a period of time, all right, we'll be keeping track of that in this conversation history. All right, so Cody interacts with the agent. Agent goes, what's the history of the conversation here? Pick up some information from that. The next step there is the agent will reach out to these other repositories, and this is what Cody called the fact to look up earlier. All right, it's looking up the facts about maybe the shoe that Cody mentioned, or Cody's order, or the return policy, or the inventory for that current item, or similar items. Lots of different things it could be looking up, but the point is, this application is going to be going to your other enterprise repositories to pull information relevant to this conversation that Cody's having with the agent. So now at that point, the agent is going to take what Cody entered into say the prompt. And while I mentioned prompt, so typically you might not want to take exactly what Cody entered as is. So a lot of times these chat applications will have templates, some predefined templates that could be used, and it will take information that in this case Cody put in the chat, put them in the right place in the template to try and get a more consistent or better response back instead of just literally sending whatever somebody decides to type into the application. All right. So at this point, use the template, taking what Cody's typed into the application, taking information from the conversation history, taking the information from the fact lookup from the other enterprise repositories. And at this point, it formats all of that into and sends a request to the large language model to basically tokenize all of this information I have about what Cody wants to do. All right. I know the shoes, I know when he ordered it, I know what's in stock, I know the return policy, I know what's been going on. So we take that, the application takes that, sends it to the large language model to tokenize it, to get that vector back. And then at that point, the application will then call your vector database where your vectors are stored to get those results that are most similar to that vector. All right, so you're looking for information related to this particular shoe and this size, basically whatever happens to be in those vectors that you've tokenized through your large language model. So it's going to return the most relevant results back to the application along with the associated documents in the vector store. Then the application will then take that response, again, go to the LLM, to the large language model, to format a response. So basically, okay, I have everything from Cody's question to the chat history to the fact lookup to the similar information from my vector database. We'll go ahead, go to the LLM one more time to tokenize that, to generate the response that ultimately gets sent back to Cody. And before we send that back, we'll update the conversation history. So if he comes back later today or tomorrow or something, all right, we know what we've already talked about with Cody. Now at that point, the application is going to send it all back to Cody. So there's a number of systems and things that come into play here with the conversation history, enterprise repositories, the large language models, and your vector database. Now we are specifically talking about DocumentDB, right? Vector search, vector indexes on DocumentDB. So using DocumentDB in this type of architecture can simplify it. Right? So your vector store, DocumentDB can store vectors, and DocumentDB can also get that other information that was previously in other systems, right? Using DocumentDB maybe as your OLAP system here for storing the information about the orders, storing information about the inventory, so you can have everything in one place. So you can just do your vector lookup on DocumentDB, and you have all of the associated information that you need in DocumentDB as well. So it can simplify, make this type of architecture easier. Okay. Has anybody done any work with RAG systems? Just curious.
Yep. Oh, I probably don't count, do I? Sorry. Quite a few. That's awesome.
That is good. That is good. All right. Cool. All right. So now we're going to shift focus on DocumentDB for a little bit. So, got the intro as to, vector search if you're not familiar with it, and a typical RAG architecture. But I want to focus a little bit on DocumentDB and some of the capabilities, and why DocumentDB is a good choice for your vector store if you're not already using DocumentDB. One reason why you may want to do that, as you see on the slide here, reduce the need for data sync and movement. If you saw on that previous slide, we're going to other operational data stores, we're going to the vector store, we're calling different systems, we got data to sync between the two. All right, with a database like DocumentDB, you have your operational data in DocumentDB, and your vectors or embeddings are in there as well, stored in the relevant documents in the database. So don't need to synchronize data between multiple systems. It's all in one system. So it simplifies it, makes it faster. And once you update it in DocumentDB, it's available. You don't have to wait for it to sync to some other system. Second reason To consider it is using familiar tools that meet your requirements. So there's two aspects to that. One is the database itself, right? Say, for example, you're already using DocumentDB, but you're not using it as a vector store or vector search use cases, right? But you know DocumentDB, right? You know how to work with it. Your operations team know how to manage it, right? And it's working for you. You know how it works, and everybody's familiar with it. So instead of introducing potentially another system to store vectors in that folks may have to come up to speed on, well, store them in DocumentDB. So there's that aspect of it. The other aspect is from coding. All right, continue to use the APIs that you're already familiar with. Again, go back to the example, if you're already using DocumentDB, all right, you're familiar with the APIs, how to access data, how to insert it, update it, query it. You don't have to learn another API to interact with a different vector database. Thirdly, faster experience to end users, and a lot of that comes down to just reducing the number of systems that you're interacting with throughout the process of this chat while Cody's trying to wait to see if he can return his sneakers and get a replacement. All right, we want to be able to get him an answer as quickly as possible. So that's going to help get that faster, less systems to interact with. And lastly, avoid additional licensing and management. So touched on that a little bit with again, if you're already familiar with like DocumentDB, you're familiar with how it operates, bringing in another database, not only do you have to become familiar with how that operates, it may have different licensing requirements, things like that. So now effectively dealing with two different entities for two different databases, whereas you could just deal with a single one. All right. Now, real briefly, we said we weren't going to, talk too much about what DocumentDB is, but just want to give a little bit of a level set here. So, yes, the focus is on vector search and using DocumentDB to store vectors. But if you're not familiar with DocumentDB, so a couple key points, as you see here, it is fast and scalable. So the architecture, it's a cloud-native architecture. Separate the compute from the storage so they can scale independently. Your storage can scale all the way up to 128 terabytes automatically with no interaction on your part. All right, so as you add more and more data, you have more and more vectors, this storage is just going to grow to accommodate that. And then at the compute layer, you manage that. It is instance-based at this time, so you do need to manage the instances, the size of those instances. All right, but you can have as few as one instance all the way up to 16, regardless of how much data you have. Right. So on the one hand, the way to look at it, you could have the full 128 terabyte data set with just a single small instance. Now, probably wouldn't want to do that for a production environment because your response times might not be what you want, but you can do things like that because of the separation of storage and compute. It is a fully managed service. Right, so all of the undifferentiated heavy lifting that you might have to do with other databases, right, we take care of that. AWS takes care of that for you with DocumentDB. It is enterprise ready, enterprise grade, 4 nines of availability, highly durable data within a cluster, data replicated automatically for you across 3 availability zones in the region where your cluster is deployed. So again, you don't have to worry about maintaining multiple replicas and all of that. It's handled for you by the database. And then lastly, going beyond a single region, we do have global clusters for multi-region workloads. So you can have from 1 secondary region to 5 secondary regions within a global cluster configuration. If you want to either reduce read latencies, right, for local reads is one use case for global clusters. Another is for DR type of use cases. If you need high availability to ensure that if something happens in this region, I can fail over to another region. And then lastly, DocumentDB is MongoDB compatible. It's in the name. So what MongoDB compatible means is we don't support 100% of everything that Mongo supports in terms of APIs and operators, but we do clearly document what we do support. So for what we do support, you can expect to get the same results back from DocumentDB, and you can use the same drivers and tools with DocumentDB because of that compatibility. Okay, just I'm not sure if we asked this before. How many folks are already using DocumentDB?
Awesome.
All right.
Fantastic.
Okay, good. So it's also good we have a lot of folks that are new to it. So glad to see you here. All right, so now that we know a little bit more about DocumentDB and some of the capabilities that make it a good choice for these types of enterprise applications, focus just a little bit here, a few moments on just some specific GenAI type of use cases that DocumentDB is certainly a good fit for. First is semantic search. All right, so for more intuitive searching, smarter product catalogs, recommendation engines, anomaly detection. We see this a lot in financial industries, and so it's certainly a good fit for those types of use cases. And then lastly, the retrieval augmented generation, or chatbots, like I walked through the architecture earlier there. So these are good fit for DocumentDB. And at this point, we're going to dive into some more of these, but on the right-hand side there, you see a couple of statistics. We do currently support 2 different types of indexes on DocumentDB, the hierarchical navigable small worlds, I said it, HNSW, and IVF flat.
I'm impressed. I can never say it right the first time, so that's good.
I don't know, I was taking a chance there. The distance metrics, and Cody's going to go into more what that means, but you got different options for the distance to determine how similar one vector is to another. Different tuning parameters that we're going to dive into in terms of creating the indexes and querying. And then we do currently support 2,000 dimensions, so can't go beyond 2,000 dimensions in a vector at this point, but anything up to 2,000 supported. All right, so with that, I'll turn it back to Cody.
Awesome. I like our slide notes. Our slide notes just says Cody in big bold letters. So
in case we forget.
So what we're going to do is we're going to dive deeper into the engine, into DocumentDB. So we saw this earlier. What I want to do is talk about what DocumentDB handles, and that's that vectorization, right? Holding those tokens. You might have saw on Doug's slide a second ago, we support 2 indexing methods, IVF flat and HNSW. So what I want to do is I want to start off by talking about these. IVF flat, we released that at around reInvent last year, 2023. HNSW came shortly beyond that. But let's start off with IVF flat. IVF flat is inverted file with flat compression. What happens here is when you create an IVF flat index, you're going to split all of your documents into different lists. You're going to specify the list whenever you create the index. You'll see that in a second. And what happens is you get this centroid that gets kind of placed in the center of those lists. Well, how many lists does it create? Well, you specify. You tell it how many lists you want. There's some trade-offs. We're going to talk about some trade-offs later, some best practices around this. But if you have 1 million documents and you have 1 list, probably not very good. The performance is probably going to be bad every time you see that. If you have 1 million documents and you have 1 million lists, why not just have a regular index? It's kind of pointless, right? So you have to kind of judge and gauge what that right value is. Again, Doug will talk about that a little bit later. But what happens is when your query comes in, your query gets compared to those centroids to find the one that's closest to it. And it starts there to find out, well, what is the most relevant document I want? Or what are the most relevant? What are the documents that have the closest value to what I'm looking for? And that's a key element here, right? Again, vector searches are not binary where they match or they don't, right? You know, you're looking for which ones have a very high recall value, what's close to it. So we have this value here, K. It's the funniest parameter value I've ever seen. Like K, clearly everybody knows what K means, right? You can tell by the name. Well, that's the number of results to return. Because we're not binary, because it's not a select star from table where name equals Cody, right? It's show me where the query is close to results. And so you have to tell it. In your query, you have to say, I want these results. I want these 2 results. I want these 3 results. Of course, you have to tell it the path. That's, well, what is the field that holds my embedding? And then the similarity. We have different distance metrics to use. Euclidean, this is a really good one for a recommendation engine. This is essentially telling you what the distance is between the end of these vectors. We have cosine. Cosine is going to tell you the angle difference between two items, and then we have dot product, and dot product is kind of like a mix between the two of them. Each one has their own use case, but for recommendation engines, Euclidean is going to be really, really popular. We're going to see that in our demo later, by the way. Probe. Probe is one that's extremely important here whenever when you're running your query. Probe is going to tell you, well, how many lists do I want to consider when I'm looking for my answers? Now, here in this example, we're confining our query to look at just one list, and I'm going to ignore any other neighbors. But you have to be cautious when using this type of index and when you use these kind of values, right? Because if your data grows a lot, as you're adding more documents, updating documents, deleting documents, well, you've created that index and that index isn't changing. Those lists stay the same. And as you insert documents, you remove documents, those new documents that get inserted, they have to live within those lists that you originally created, right? So if you had this document that was contextually relevant before, your lists are still the same, you might have other documents that match better, like they're even closer. But remember, you're confining to one list, so you're missing those. Those 3 documents might be a better choice. You've inserted a lot, you're gonna miss them because you're just looking at that one list. You'd have to expand that list, right? Or you have to re-index, but we'll talk about that more in just a second. The other index that we have is HNSW, which means
Hierarchical, navigable, small world.
Thank you. I didn't have to say it. What Doug said. Yeah. Essentially what you're doing here is you're organizing these vectors into a graph. Key differentiator here is writes are iterative. That means that training is not required like it is on IVF flat. In other words, I don't have to build my index after the fact. I can pre-build my index. And that's going to become important as we talk about this later. Query comes in, it's compared to the highest layer of the graph, and it moves down until it has enough neighbors to figure out what the answer is. Really big values here. Just like K, we have this fantastically named variable called M. Any ideas what M means? Yeah, I didn't know either. M is telling you how many of my how many links I'm going to make between my documents. So as I'm building my index, how many different of the white lines am I making between those documents so that they have that connection that it can traverse. EF search is telling me how many neighbors I'm choosing to build my edges, to kind of build this network. Think of it this way. On your street, you have your neighbors. You have neighbors on either side of you, you have a neighbor across the street. And somebody comes to your house and they say, hey, I'm looking for John Smith. Do you know where John Smith's house is? Well, I know that person's not John Smith. I know that these people aren't John Smith. So I say, I don't know, but hey, ask my neighbor next to me. They might know. So they go to my neighbor and they say, hey, do you know John Smith? I don't. Ask the person next to me, right? They have to traverse those houses because we're all very antisocial neighbors. We don't know who each other is beyond our next door neighbors, and it takes them a while, right? Now, if I'm a social butterfly and I know everybody on my street, I have 20 houses on my street and I know what every person is. They come to me and they say, hey, do you know where John Smith is? I'm like, yes, I do. 13 houses that way. He has the blue truck in the driveway. That's John Smith. The trade-off here, as you can imagine, is it takes a lot of memory for me to remember 20 neighbors and who lives where, right? And as I'm getting older, I have kids that are getting older. I'm finding my memories going away. So it's harder for me to remember these things. But that's the difference here. That's what EF search is doing. When you query this HNSW index, you have this EF search value. And this is kind of the opposite of that. It's similar, but it's opposite. This is saying, how many of those neighbors' houses am I going to go to find John Smith? So think of it this way. If my EF construction value is low, I only know the people left and right to me and the person across from me. I better have a high EF search value to offset that because I'm probably going to have to go to a lot of houses to figure out that value. However, if I'm a social butterfly, I have a very high EF construction value. I know a lot of my neighbors. My EF search value can probably go way down because I'm going to find it a lot quicker. I'm going to use all these links. On one side, it's when we created the index, EF construction. On the other side, it's EF search when we're searching. So think about that context. Do I want to put all the work on that one-time index build, or do I want to put all the extra work on every single query that goes into it? Again, we'll talk about these trade-offs a little bit more when Doug goes over the best practices. But this is great. We have two different index types. We've kind of gone over the highs and lows. Which one do I pick, right? We have reasons for each. Well, this one, IVF flat, it's smaller. That's fantastic. HNSW uses more memory, but it might be better for our queries, especially if I have fast-moving data. Generally, you're going to get better indexing, faster indexing with IVF flat, whereas HNSW is going to be considered easier to manage, right? HNSW is generally what the better choice. It gives you that better query performance, especially when you consider that trade-off between speed and recall. But if you have relatively static data, remember the example I gave you earlier was we're looking at our policy document. Our chatbot had to go read a policy document. Policy documents probably don't change very often, so it's not a big ask to re-index when it does. So if you have relatively static data, IVF flat can be a fantastic choice. If you need exact nearest neighbor search, exact is a keyword here, don't use vector index. If you need exact, just use a regular index. Recall value, I guess recall value technically could be 100% if your query exactly match a document for an answer, but that's probably not the case. So don't use a vector index if you need exact match. If you need very, very fast indexing, IVF flat is a great choice. Whereas if you need that easy management, you have very busy data, a lot of updates, a lot of deletes, a lot of inserts, or that high performance with recall rates, HNSW is a great choice. Fast indexing, we didn't talk about that. Well, what's the difference in indexing speed? Kind of give you an example here. It was a test we ran to show you, we have our data, we have our embeddings, and we're gonna create an index on this. Create an index for HNSW and an index for IVF flat. Clearly, and I promise you, IVF flat is on there, you can barely see it at the bottom, the green. Clearly, IVF flat is a lot quicker than HNSW. Multi-threaded, that's key here. Now, we ran this on an 8x large instance. An 8x large instance is you're able to specify multiple workers in DocumentDB to create an index. You can create, you can use up to 50% of the number of vCPUs as workers to create an index. And an 8x large instance has how many vCPUs?
I'm going to say 32.
Oh, let's go with that, because I don't know without looking at our product page. We'll say 32. So that means that I can create 16 threads to create that index. Obviously, it's going to go a lot faster. But what if we accommodate for that? Like, what if we say on an individual thread level, how much faster is it? Well, even on an individual thread level, IVF flat is significantly faster than HNSW. So there is a trade-off here. However, remember, IVF flat, we have to have data, or we should have data before we create that index. Whereas with HNSW, it doesn't have to be pre-trained. We can create the index first and then insert the data. So how big of a difference does that make? Well, obviously, creating the index first is a much better idea, right? If we in the first test, what we did is we said, we're going to insert the data and then create the index on top of it. In the second situation, we said, create the index first and then insert the data on top of that. I might have said that backwards, but regardless, you get the point. Clearly, creating that index first is better. Even though index builds on HNSW indexes are single-threaded, inserts aren't. You can multi-thread inserts and take advantage of HNSW. It will handle those. But with that said, we'll move over to best practices, because there was a lot of important information, a lot of variables to consider there. So Doug?
All right, thanks, Cody.
Oh, I'm sorry, I just progressed you forward. I spoiled it.
That's all right, yeah, you gave away the surprise. All right, the surprise is that vector embeddings use space, as you can imagine. Now, this is maybe not something you might necessarily think about at first, but it certainly can have implications. You may want to have the max number of dimensions in your vector for the most how do I say, the best results, the best search results. But the trade-off is the more dimensions you have, the more space that embedding is going to take, right? And again, we're embedding these vectors in our JSON documents in DocumentDB. So you see an example there on the top left. The embedding is in the field called embedding, and there we see the beginning of this array of all the dimensions. Now, just to quick formula there that you can use to kind of just get a quick estimate of how much space this will add to each of your documents. So that it's your key length, right? The name of your key. In this case, it's embedding, which is 9 plus 1, so 10. And then for each dimension, it's 13 bytes. So pretty simple math. 100 dimensions, about 1.3K, so on and so on, up to 1800, 23.2K. Now, again, it's a trade-off. You don't want to just go to the maximum because, A, more is better. More is going to create larger documents, and that has its own implications. So we're not going to go into all that right here today, but I think I see at least 1 or 2 people that were at our DAT320 yesterday, and it's coming up again
Thursday.
Mm-hmm. DAT320. We're going to really dive deep into document sizes if you want to hear more about that. But that's all I'm going to say about that for now. But just know the more dimensions in your embeddings, the larger your documents, all right, and it's a trade-off, right? Bigger documents can lead to slower performance in some cases. All right, so think about how many dimensions you need in your embeddings would be the first key takeaway. All right, don't just use the max. The second is there's a lot of stuff on here. So I'm going to try to make this simpler. But ultimately, it comes down to what is your goal, all right? Do you need searches that are optimized for the lowest latency, lowest resource usage? Do you need searches that are optimized for the absolute best possible recall? All right, I need this to be like as close to 100% as possible. All right, or you just need a balanced mix of these two. So if we start with HNSW and start in the middle there, balanced. So these are default values. If you don't specify M or EF construction when you create your index, these are the values that will be used. So 16 for M, all right, so 16 connections, and 64 for EF construction, meaning we'll consider 64 neighbors, all right, in this index. Now, for HNSW, if balance doesn't work well, so before I go any further, start with balanced. Start with the defaults. If that gives you what you need, great. There's no need to go higher or lower. All right, you could probably stick with that. But if it isn't giving you what you need, right, it's consuming more resources than you thought. So then you want to go up to this top row. So optimize for memory and latency. So you want to reduce the M value. Right? You want to reduce the number of neighbors. Like Cody, I'm getting older, unfortunately. And memory doesn't work as well as I used to, so I don't remember who all my neighbors are. I can remember maybe 3. I can't remember 30. So my M value is lower. So you want to reduce your M value a little bit. You want to reduce your EF construction value a little bit. Basically, you're keeping track of less information, so it's going to consume less resources. It's quicker to scan those indexes. And then for EF search, when you go to query this, execute a query against this, all right, you'll want to bring your EF search down as well. All right, so start with a balanced. If it's using more memory, more resources than you expected, maybe you can start bringing those other values down. Now, if you start with balanced and you're more worried about recall and you're not getting the results you expect, well, the inverse, right? Just increase those numbers. Right? We want to keep track of more neighbors, right? We want more connections. And when we're searching, we want to consider more of those, right, to get a better recall. Okay, so that's HNSW. IVF flat is a little interesting, to be honest. I had to look at this for quite a while to get it straight in my head, but let's start with balanced. So there's no default values per se. You do have to provide a value when you create the index. But the recommendation is if you have a data set that's 1 million documents or less, your list's value should be the square root of the number of your documents. Right. So basically, how many groups in that slide that Cody had that had, I think, 5 or 6 different lists with the documents, that's what this list's value is. If you have more than 1 million, the number of docs divided by 1K. All right, so A little bit different math depending on how many documents you have, but that's a good starting point for lists value when creating an IVF flat index. Querying is the number of probes. Think of that as how many of these lists am I going to consider when I'm querying. So for that balanced approach, good starting point, probes should be the square root of the number of your lists. Right? If you wound up with 64 lists, well, 8 probes is a good starting point. Okay, now, depending on which way you need to go, do you need to get better recall, lower latency, lower memory usage? All right, so if you need to reduce memory usage, get lower latency, increase the number of lists when you create the index. So at first, like I said, it seemed a little counterintuitive to me, but if you increase the number of lists, each of these lists actually have fewer items in them. So there's less to scan, less to maintain in each of these lists. So increase the number of lists, and when you query, reduce the number of probes. So I've got more smaller lists, and I'm going to search fewer of those, effectively searching through fewer embeddings to try to get my match. All right, again, recall may suffer, but in this scenario, you're trying to reduce your resource utilization, your memory, reduce your latency. Okay. Now, on the other hand, if I need better recall, well, reduce the number of lists. All right, so now I have more items in each list, but increase the number of probes. So more lists of more items is a good way to think of it. I'm going to have better recall because I've got more that I can search through to try to find what I'm looking for. Okay. So if you didn't take a picture of that, I'll give you a second to take a picture. All right, so again, start with the balanced values. It's really easy with HNSW because those are the defaults. With IVF flat, you've got to do a little bit of math. So what does this look like in terms of performance, right? The charts and graphs that Cody was showing, the different metrics there, was for index builds. So this is performance. This is actually querying. All right, we've got the indexes. Now we want to do some lookups on these vectors. Now, if you look at the top, we've got 10 million documents, 128 dimensions in our vector, so not terribly huge. In this case, we've got 3,000 lists. Right? So that's a good way to think of that. That 10 million documents is broken up into 3,000 groups. And this is the largest DocDB instance we have with 96. Oh, sorry, it's not, because this is double. So 96. Oh no, this is threads, not workers. So I stand corrected. So this would be like a 24XL, which has 96 vCPUs. So we use the big AND test, the approximate nearest neighbor. It's like benchmarking. So really the purpose here is not to show how we compare to other vector databases, but to help visualize the impact of these different values. All right, and ultimately there's a point of diminishing returns. As you see here on this slide, on the bottom we have the number of probes. Right? When we start with fewer number of probes, we can have much higher queries per second. But our recall in this case is, what is that? 80-ish, 85% or so. I mean, maybe that's okay for your use case, maybe not. So in this case, okay, we bump up the number of probes to 40. All right, our queries per second go down because we've got more to scan. We're utilizing more resources. Queries per second go down, but our recall goes up. And as we go across to the right, so the other thing to keep in mind, it's not going by 20, it's kind of logarithmic, sort of. It goes by 20, then 40, then, 320. But the point is when you get to around 400 probes, anything after that, increasing the probes doesn't really give you any better recall. All right. So, and again, that's for just the specific workload, but you can see that after a point, yeah, you can increase the number of probes, but you may not get any better recall, and you're actually getting lower performance. All right, so you'll definitely want to test this out. So that's IVF flat. And HNSW, similar. Across the bottom is EF search, right? Basically, how many of those neighbors do we want to consider when we're searching? Right, when it's 20 queries per second is great, but as we go and increase the EF search, we can see the recall increasing, getting up to close to 100%, around, I don't know, I'll say maybe like 300 for the EF search. But again, after that point, yeah, maybe it goes up a little bit, but can you afford to take the hit in the queries per second to get that little bit better recall? So again, just something to keep in mind. Start with the defaults, bumping up EF search or lists. You probably don't want to go to the maximum right away, right? Just bump it up little bit by little bit until you get to the recall that suits your use case. Okay, and with that,
oh yeah, fun
turn
part.
it back to you. Demo time.
I've learned that at reInvent, it's probably a bad idea to do live demos. We have tens of thousands of people on the Wi-Fi that I'm sharing with you as well. So we're gonna go through a video that I recorded of a solution. And what I want to show you is really the art of the possible, what you can do with this, kind of using some of what we talked about here. So we're gonna look at an interactive Python notebook that is setting up a RAG architecture. What we're doing here is we're just importing all of our LangChain libraries. You can see that we're setting up our HNS-W index. Again, pre-creating this here, cosine similarity. We're gonna chunk our data up. We're gonna create chunks of 1,000 1,000 bytes, overlapped by 200. We'll talk about that in a second. What are we chunking? Well, for this example, we're chunking the public material for DocumentDB. We're looking at our developer guide, the PDF version of our developer guide. We're looking at our ebook, our data modeling ebook that we just created. We're going and grabbing all the public pricing pages, the FAQ pages, our customer pages. And we're going and we're grabbing every single DocumentDB blog that was written. And we're chunking that up. This is our large language model that we're passing it through to create our embeddings. And we're chunking that up into 1,000 text chunks. Some are going to be less or smaller than that because we're going to delimit it by paragraphs and certain characters. I'll show you an example of the collection here in just one second. And that's our domain-specific data, right? That is our data that we're using a large language model to help us out with that. Here, what we're doing is we're creating our chatbot to interact with. And we talked a little bit about prompt templates earlier. There are probably 5 sessions here at reInvent about prompt templates. Prompt template is deep. It can go very, very deep. But you can see we're telling it to, be professional. If you have code samples out, format it correctly. This is our DocumentDB collection. So once we have all that data and we're inserting it into the collection, we're keeping it in this DocDB KB namespace. Here's our HNS-W index, the only index we have other than this _ID. You can see our average object size, we talked about that earlier, was about 13 kilobytes. And if we go and take a look at one of those records, I'm not going to include the vector in it because I don't want to show you 1,024 numbers. It wouldn't fit on the screen. But just kind of give you an example of what this looks like. Here's a piece of data. So it took just that piece of content. That's where it came from. This data modeling ebook, that's the page. You can see it's really small. That's not 1,000 characters. Well, we're using certain delimiters in there. We're using paragraph endings and sentence endings. So to look at what we'll do is we'll look at a couple other ones, show you some ones that will have bigger sections of text. Man, this guy typed slow, whoever did this demo. Okay, we should probably make that pretty because that's kind of hard to see. So if we can add a dot pretty to that. There you go. That gives you an example. So we have this text content from the developer guide. We can see this one came from that developer guide on page 112, but this is our domain-specific information. This is what we're using for our RAG application. All right, so what is our RAG application? What are we doing? Well, we just created a DocumentDB chatbot. We can ask questions about it. We can say, okay, well, we'll start off, what are the supported regions for DocumentDB? So that query is getting embedded, and it's being compared to our data in DocumentDB to return data. Now remember, we've taken all the public data, and we're just helping it out with that LLM. We're helping it out with this chatbot to give us these answers. What is the maximum number of allowed collections And it knows that we're talking about DocumentDB. I didn't have to tell it. It says, well, you can have 100,000 per cluster, right? This is great. Write me a query to create a partial filtered index. I have never in my life written a MongoDB statement correctly the first time. Like, I have been defeated by brackets so many times. I cannot tell you how many times I use this to write me queries. It's fantastic. I don't have to think about closing my brackets. And so what it's doing here is I gave it some directions. There we go. I just copy that and I can paste that into my, my shell. What are the benefits of compressing documents smaller than 2 kilobytes on DocumentDB? DAT320. Come to that session on Thursday if you didn't come to it. We'll talk about why. But I can also ask my chatbot here. You have reduced storage costs, improved performance. Another great feature that we have with this is you can troubleshoot with it. Now we can say, my DocumentDB instance has very high CPU usage. The buffer cache hit ratio, it should be about 100%. It's at 50%. What does this mean? What do I do? How can I troubleshoot this? And how can I improve performance on my DocumentDB workload? So now I'm just a user. I just have this running. I don't want to go parse through these huge development guides and look through all this public material and read all these blogs. I just ask it a question using, again, my domain-specific data. And now I have steps. Scale up my instance, optimize my queries, increase my buffer cache hit ratio. And I can dive deeper into that at any point. I can ask it to go deeper into item 2. Well, how do I increase my buffer cache hit ratio, right? Chat history is in here. We're keeping a record of the past, I think, 10 history values to consider when we're answering them. But that's another variable, and I think that's kind of what I want to end on. That's what I want to talk about here is, in DocumentDB alone, there's a lot of variables, right? There's EF search, there's EF construction, there's M. Who remembers what M is? Exactly, yeah. I have to look it up too. We have K values, how many items we want to return. We have list. On top of that, we have to choose our LLM model. What was the name of the new one we had? Nova. Thank you, Nova. We have to consider what is the LLM that we want to use. What is the chatbot agent that we want to use? How big are our chunks? How much overlap do we want, right? It's an overwhelming amount of variables that you have to consider when you're making these generative AI solutions, chatbots like this, right? And I think that's what I see a lot with customers. It's information overload. You just don't know where to start. My recommendation is just start. Just create something. If you don't know where to start, we have help. So these first 2 links here, we have a GitHub repository that actually has some interactive Python notebooks that you can use to build something very, very similar to what I just showed you. It's going to be slightly different, a little bit simpler, but go check those out. Plug in your domain-specific data. Learn those code samples and see what they're doing and start adding your variables to it. Change the model. Change the LLM. Change the chatbot agent. Change the number of vectors. Like, play around with it and see how it affects things. And it's very interesting because I was talking to Doug about this when I was creating that demo, when I was writing that code for the video we just showed. I was using one model and getting dramatically incorrect answers or incomplete answers. And all I did was I changed the model. That was it. I didn't change anything else. I just changed the model and I got all of these answers. So it's crazy how much the model can affect us as well. That data modeling ebook, the one that I use to support this, to give us our answers, you can check that out. That's on our public page. Skill Builder, if you haven't checked that out, if you're kind of introducing yourself or getting familiar with DocumentDB, we worked with the training and certification team. We've written several courses, all the way from introduction to DocumentDB up to performance tuning and how to write schemas and data modeling. So go check those out. A lot of information here, but I want to stress this. If you don't know where to start, or this looks cool and you just don't know what to do and there's too many variables to choose from, start there. And I'm going to try to make, or I'm not going to try to, the sample I just made you, the DocumentDB bot, I will make that available publicly out on our GitHub as well. It's not there yet, but I'll make it there. With that being said, thank y'all so much for joining us. Please, thank you.
Thanks.
Please fill out that survey. Let us know how we did. This is how we get better. This is how we improve. And come check us out, DAT320 on Thursday. Thank y'all so much. Appreciate it.
Take care.